Bon après-midi tout le monde. Bon après-midi. L'offre Tuyen Tran. Donc vous avez présenté votre travail de thèse. Mes collègues m'ont demandé de critiquer donc, le sujet de votre thèse. Et c'est avec un grand plaisir de le faire. Alors, donc on va procéder de la manière suivante. Vous allez d'abord présenter votre travail pendant à peu près 3 heures. Ensuite, je présenterai le nom des écrits. Et ensuite, on va commencer la séance de discussion. Voilà. Donc, vous avez la parole pour 3 heures pour présenter votre travail.
Thank you, President. Thank you, all of you. I'm very happy and so glad to be here to present my topic that relates to the long-term stability evolution of underground construction, such as deep tunnel. By taking into account the uncertainties and variety of rock masses. My name is Tuyen Tran. And this work was done by under the supervisor by Professor National of Art, Dr. Lupido from the laboratory of mechanics, Gabriel Lade, and Dr. Minoku from Andhra. My presentation will begin with an introduction in which I shortly represent the industrial and scientific context of my thesis as well as its objective. Then I will focus on the chosen methodology and next two main parts that relate to the long-term stability of tunnel in uncertainty as well as variability problems. Last but not least, some major conclusions and perspectives will be drawn. Let's start with the first part. Now, the research related to the ongoing project called the CZO. It will be construction in next year, and it is a disposal center for radioactive waste storage. It is designed to store high-level and long-lived radioactive waste produced by all current nuclear facilities until their decommissioning, and by the processing of spent fuel used in nuclear power plants. The storage is scheduled to be set up in a very tight rock called Carbo-Oscordion or COX. This place is located in the depth of 400 to 600 meters. And close to the project, there is an underground research laboratory URL in North Otmani from Andhra, and many research about this cell extracts and study by various researchers in both laboratory or in field. And in this underground laboratory, they consist the computing facilities and environment observatory. This meet the CZO scientific research needs. And the system of URL here is shown as the 3D network excavated in the cell itself at the depth of 490 meters, where all depths are orientated mostly following two direction, parallel or perpendicular to the major stress, and this stress is larger than 1.3 compared to another stresses. And these stresses often approximate about 12.5 ampere. This extensive observation and test allow us to have more and more idea about the behavior of stable rock and rock masses. And this will reduce the activity linked with its behavior. That they have demonstrated some features that they are in center of this work. For example, in this figure, you can see the convergence of two DCR and DCS in both horizontal and vertical. They show the dependence of the time dependence of displacement is also clear. And for the table, you can see here the observers of dispersion of uncertainty of the rocks property. For example, here the Young-Rulus E with the mean and the standard deviation. It shows that the standard deviation is about 60% compared to the mean value. Indeed, you can see over here there are several figures show the another uncertainty. It means the variation of Young-Rulus can vary according to the depth or according to the space in many space. So the uncertainty is in general are so important and need to be considered more. And in literature, there are some uncertainty sources like mapping conditions, geometrical properties, and geometrical parameters. And we focus on geometrical properties. It can be classified in two types, the epistemic and the allegoric. And the first type comes from the measurement error or the adopted model, for example, an extrapolation at long-term clip model. When we say about the uncertainty problem, it means this type. And why in another case, when we consider the variability problems, it means we want to talk about the spatial variability. It means the variation of time of space is much more important than the variation of time. And the consideration of this uncertainty in the tunnel design is an essential task in underground construction. And in general, they have two approaches. The semi-probabilistic approach, since they often use the partial safety factors, and this approach is can consider the uncertainties in the qualitative way. However, in the probabilistic approach, they can consider the uncertainty by the propagation and on the probability of value on a structure. However, most cases often used in the short-term behavior of mass. And the question here is how to quantify of the uncertainty of the time-dependent behavior of rock masses and its propagation on the stability and long-term of uncertainty structure, such as the reef, is my main objective of my research. Due to the complexity of the problem, I precise the scope of study here. Firstly, we concentrate the uncertainty and probability of the properties of rock mass only. And this uncertainty can affect the stability of the concrete liner. The stability here can be understood that through the acceptance probability of the stress state in the liner regard to an allowable stress, such as in this function. And this function with Z can separate the domain to the safety and failure domain, where the maximum equivalent stress here it depends on the random variable x, and that is the rock mass property, and we consider it in the period of 100 years. This is a practical design, and this also an exploitation period before the closure of deep tunnel in the context of nuclear waste disposal. Lastly, we consider only fully mechanical behavior. To make you better have a good overview, I showed you my workflows of the thesis. First part, I will need to find an appropriate method by studying the methodology, and then I need to validate it and check the efficiency of this method by using some academic example and apply our test with the closed form solution in the linear visco rock, and we apply it into uncertainty problem as well as variability problem by applying this method to assess excitant property of tunnel in the viscoplastic rock using the limit model. I will detail now the methodology of conduct long-term stability of the brick. First, I will brief summary some common reliability analysis methods, and this can group in three methods: local, sibling, and global reliability methods. Probably almost you know the sibling method with the well-known cone multiple simulation, and these types can provide an exact result if it has a sufficient sample. And for the local reliability method, it approximates it at local approximate the performance function, and this often use the norm of design point or most probable value point. And for the global one, it's often use the meta model, and it approximates the global function by surrogate model. And in this method, we select the prediction-based method because it not only provides the the best estimate value at an entire point, but also it can give us the prediction variance or prediction uncertainty. To clarify the AKMCS, it means we combine when we have a shallow grazing model, we can apply the grazing, apply the multiple simulation to compute the failure property or the incident property, as you can see in the flow chart. But I want to focus on 2 points. The most important point is related how to define the best training point or the next best point to act. It often called as a learning function. And after that, we have another important point, that is a stopping criterion. It's related to the learning function that we selected before. And the fact that in the literature, the classical AKMCS has some drawback. So we have a new proposal. It's called modified AKMCS. we use two conditions. The first condition that the new training point must close to the border. It means it on the close to the limited function, and it must be far from the other points that we have already taken before. And we test it and we prove it have some fast conversions. So now it's time to validate and apply the new proposed method to uncertainty problem when we assess the long-term stability of structure. Firstly, to verify our proposed method, we consider the circular double liner tunnel under hydrostatic field in viscoelastic rock, and we assume that the domain will have infinite ordering. True liner is works with the elastic behavior and can put in the different time, T1 for the first liner, and T2 for the second liner. As over here, why the rock mass work with the Boxer linear viscoelastic, which you can see here. This is a model as the series of the Kevin model and Maxwell model. There are 4 parameters that can describe the time dependent of rock mass. And thanks to multiple simulation, we can validate our modified AKMCS to consider 4 parameters here, and its effect to the existence probability at long-term of tunnel. Over here you can see when we compare it to the direct multiple simulation, and we also compare with the 2 classical of AKMCS. Our proposed method is nearly a half of 2 classical methods, and this also provide a good result. As you can see over here, our proposed method in the pink colors, and it's nearly a half. And especially in the case when we use in each iteration, we use a subset of code as in this figure. When we select 4 simple points in each iteration to up, the result show it is optimal, and it's very useful in the case of parallel computation, and it's useful when we use the numerical solution. Over here is an application in geometry analysis with the tunnel work with the Bucher rock viscoelastic, and on the first figure you can see the monotonic of existence probability with the time, and it's changed quickly when the techniques reduce. And for the case of this figure, you can see when we consider both of liner thickness, the first one and the second one, when we use the minimum of thickness, it can have a maximum of probability. It means it can get 100%. And for the case of the installation of 2 liners with the property of existence can have a significant if we put them together at the same time. It means in this example it has 5 days, and when we keep, for example, we keep the one value of the first liner, the second liner can be safely when we put it in longer time. And now I would like to show you the problem statement of ring excavated in the COX rock, as I showed you. This is an example of a ring. For example, that parallel to the major stress, and this is from the URL also. And based on the symmetry of the geometry, we select one pattern as in this figure, and we use the boundary to displacement at the left and on the bottom, y in the top at the top, and the right we apply the initial stress equal to 12.5 amperes because it generates parallel to the major stress as I said before. And this radius we select as about 5 meters, and the boundary must more than 10 times to have no effect of the boundary. The two liners have can put at the time of can put together at the time which correspond to the deconfinement rate at 85%, and the first liner we use the compressive liner. It means this material can absorb the conversion and reduce the transmit radial stress to the main concrete liner. And why the concrete liner we use only the elastic linear. Why the rock mass here we use to describe the COH rock by the viscoplastic model, and we select the model of limit. The computation we use by the numerical called cos aster by EUF. For a compressive material, we use the linear elastic behavior, whose mechanics can be described by linear elastic, such as in this figure. The fact that this figure we take from the literature, and there are three main parts. First part, the stress can quickly increase, and they increase slowly, and in the when they have 50%, they change quickly again, and then we propose 3 liners and with 3 jump rules, and the volume which strain V2 we call the compressibility of material, or the compressible potential. To apply it with the viscoplastic, we must select model called limit, which you can see as in this formula, where the visco rate can be described by the deviatory part, a function of deviatory part, and this function can be transformed to another form that we call the cumulative viscosity, depends on 3 parameters A, B, and C. And as in this function, where 3 parameters can have a function of triple parameter of the limit model. We use 3 grid tests on the COH rock properties, rock samples, and it's possible to characterize the mean and the standard of A, B, and C of the limit model. The video taken from the literature describe the tri-axis grid test, and with regard to 7 applied deviatory tests, and we perform the sample taken from the same geological horizon, and the Poisson later here is nearly low significant impact, so we consider it as the deterministic parameter, and we consider here the Zagorus also taken from the literature, with the mean and standard deviation. So we have four parameters A, B, C, and E are considered as random variables to consider the uncertainty. And since we have the mean standard of three parameters here, as well as the correlation matrix in this table, we can assume it work with normal distribution. The main reason for using the viscoelastic model limit lie in the number of parameters. Here we use the deterministic problem first to apply this model, and you can see here for the first few days it changed very quickly, and after 10 years it nearly not changed too much, and this describes the evaluation of the maximum sigma stress equivalent with vary with the time, and it also variation with the thickness, the second thickness, and it shows cost when the thickness reduced, the stress increase in the blue curve, and when we take only 100 here, we have another figure as in the right side. And we also apply the case when we take for parameter of its mean value. We consider the compressive potential, and we show it have shown that only the first case when the epsilon v1 equal epsilon v2 equal the 0.115, we have the significant result for the maximum sigma equivalent, and this is one linear case as in this case, and all case here you can see the volumetric strain has lower than 12%. For the case of another set, we also consider the effect of the compressibility. It has some different result, and it also means that the factor have a strong effect to the sigma equivalent at the maximum. And over here, when the volumetric step overcome the compressibility of the liner, the step change quickly. So that's why corresponding to the maximum of the concrete liner is also changed quickly. To apply it in the method in the reliability analysis problem, firstly we consider with the threshold of the concrete, we use the C60 of S in the 0.2, and this figure shows the change of the excitant property when we change the number of iteration, and this about 90. It has the convergence, and it's also in this figure we also consider the parametric study of the sigma, the threshold or the limitation of the stress. It exponential reduce when the stress is reached, and this figure shows when the threshold over than 27, the probability lower than 1%, and for the orange curve show the number of computation, and it change very quickly and get the significant value when the probability is so small. And for another result of reliability analysis problem, we also consider the parametric study on with the major factors such as the thickness of two liner, the confinement rate, and the compressibility. For the first thickness about first liner, as you can see, this change a little bit from the 6% to this value, and it also can be lower than 1% when the thickness over 14. And compared to the case of the second liner, it's much more important than compared to the first liner. And for the case of the confinement rate, it's quite changed a little bit. And for the last case, the compressibility is very significant when epsilon V1 is equal to epsilon V2. It means only one liner, one Zaporozhye of the first compressive liner. And now let me to go to the second main part related to the variability problem. And firstly, I will show you some instruction because it needs to have the node of random fields, and it has the problem, the same problem such as in the uncertainty problem, and it have a little bit different. When in this case it have a spatial variability, so it should be use the node of correlation length, in which we use this node to apply the correlation function as in this equation. And the function we use here is the square exponential autocorrelation. Since we have this function, we can use this to describe the four random field with the same correction length. And the random field is a continuous, so we must characterize this by using a method, and we select an expansion of optimal linear estimation because it's quite simple and it can provide a good result after some with few expansion order that I will show you later. For the highest number of random fields, we must use another approach called the HDMA2. It's high dimensional model representation method. And now to apply the optimized linear expansion, we use in this table this characterization of random field by this method leads us to have an expression provide the random field in every point of group mass, and we must have a number of truncate expansion order we call n, and this depends on the correlation length and the variant errors epsilon. And in this case, for an isotopic case, we use for correction length at 15 meter, and we also take the 25, the same at in the isotopic case with another correction length at here. In this table, you can see here when the correction length reduce, the number of variable of each random fields change quickly, and for the case of small is really quickly, very significant. And we apply it in the first case of isotopic case. This is a figure shows the value of the coefficient A in space, in every point, and we consider it by the variance error must be lower than 5%. And for anisotropic case, we have also quite similar, but in this case, because the correlation length of y-axis is so smaller compared to the first one, so you can see it's significant change when we see in the y-axis. and it's also see in the variant errors. It might be also lower than 5%. This we apply it in some deterministic problem, and we compare to the uncertainty that I said in the first part. And in this case, you can see the radial stress is the same when and it corresponds with the radius of tunnel. However, in the case of isotopic, the stress change in every time, everywhere. It even more significant when we consider the anisotropic case. For the reliability analysis problem, we must firstly we consider two random fields A and E, because as I said before, when we use the random field with the number of correction length is small, it needs to have a significant of variable or the number order of expansion, and in this value it also shows the exponential reduced when we consider the threshold of the stress on the second ladder, and it compared to the case of isotopic case, it's so small, and it can also get the lower 1% when we take 27 of the 27 MPa of the threshold. For the case of 60 MPa, we have an evaluation of accident failure, accident probability, and you can see here is about more than 70 iteration. For another approach with regard to the anisotropic case, we have the similar exponential reduced curve, but in this case it's much more lower than in the isotopic case, and it's with the lower value it must have also significant number of computation, and also we consider it here with the evaluation of the property regard to the number of iteration. It's much more compared to this case. For some result of the durability analysis problem, when we use all four parameters for random fields with the parametric study of the correction length in y-axis, we change it from 50 to 15, and the number of variation it change quickly from 4 up to nearly 50, and the accident probability reduced as well. And this figure shows the table in the change of the probability and the number of correction length. As you can see here, is the number of cone regard to the number of the correction length in y-axis. For the case of number of variable mass more than 50, we must use another approach called the HDMR method. It's important when we use the HDMR1 and or HDMR2. We use the two terms of this original function, and in this case we can combine the predicting method to compute it in each meta model. Is very useful and have some advantage. As you can see here, to clarify the method when we use AK HDMR, there are some differences compared to the AK MCS that I mentioned before. There is 2 points here that are two design experiment, and we must use answer points. That is different compared to the last method. And we apply this AK HDMR to firstly uncertainty problem with tunnel in the viscoelastic buildup. As you can see, for the first case of cadmium one is the have a conversion soon, but the